Hello students. Welcome back to your physics class. In our last class, we discussed measuring tools. How to use measuring tools appropriately. Derivation of the dimensions of physical quantities. Now, before we move forward, let us review the lesson objectives. By the end of today's lesson, you will be able to explain the concept of work, calculate the work done, given a force and displacement it produces in its direction, define power, calculate the power in watts given an applied force and the time it takes to produce a displacement. Are you ready? Let's dive in. I know you hear things like, I am going to work, or I work in the hospital. This is how we term work in our everyday lives because the activities needs physical or mental effort. However, in physics, we say work is done when force is applied, causing a body or system to move to a certain distance. For example, if we use a rope to drag a box across the floor, the box is the body, and the force you are using to pull on it is an external force. So, let's say you are pulling on the box by dragging it straight behind you, parallel to the ground. If you use the rope to pull the box for 2 meters, we will say that you are doing work on the box. Therefore, the amount of work you are doing is equal to the force you are using to pull the box, times the distance you moved it. For example, if you pull the rope and therefore the box, with a force of 50 newtons, while you moved it 5 meters. With the unit of work being joules, when the force is measured in newtons and the displacement is measured in meters, then we will say that you did 250 joules of work on the box. Moving on. There are cases where the force applied and the direction of the object are not the same. Sometimes, the force you apply to an object won't be in exactly the same direction as the direction in which the object is moving. Like, if you try to drag the box with your hand higher than the box, so that the rope is at an angle to the floor. In that case, the box would move parallel to the floor, but the force would be at an angle to it. Specifically, you must separate the force you are using on the rope into its component parts. One that's parallel to the floor, and one that is perpendicular to it. To find the part of the force that is parallel to the floor, that is, the one that's actually pulling the box forward, you just have to multiply the magnitude of the force by the cosine of the rope's angle to the ground. So, to calculate the work you did on the box, you multiply F by the cosine of the theta, and by the distance you move the box. That's one way physicists often write the equation for work. They will set it equal to force times distance times the cosine of theta. Bear in mind, this equation will fit any scenario that involves a constant force being applied over a certain distance. Now, let us also look at work done in a force field. Sometimes, when we lift an object or a body vertically upwards, this body is pulled towards the center of the earth by a force known as the force of gravity. Therefore, to lift a body or a load through a height, a pulling force must be applied in order to overcome the weight of the body or the force of gravity. So, in this case, we say that work is done against the force of gravity or the weight of the body. In other words, work done against gravity is equal to the product of the weight of the body, m, acceleration due to gravity, g, and the vertical upward displacement, h. For example, a man lifts a weight of mass 30 kilograms at a distance of 4.0 meters. Find the work done against gravity. Take acceleration due to gravity as 10 meters per second squared. Solution. Work done is equal to 30 kilograms times acceleration due to gravity, 10, times 4 meters. This gives us 1200 joules. Again, in the case of a body falling freely in a force field. If a body of mass, m, falls through a vertical height, the work done by gravity on the body is also given by mass times acceleration due to gravity times the distance of the fall. For example, a ball of mass 10 kilograms falls from a height of 3.0 meters. Calculate the work done by gravity on the load. Take acceleration due to gravity as 10 meters per second squared. Solution. Work done is equal to mass times acceleration due to gravity times the height. Therefore, work done is 300 joules. Well done, students, you are doing amazingly well. Now, we will explore the concept of power in relation to work done. Power is defined as work over time, and it is measured in watts. It is used to measure how much energy is converted from one type to another over time. So, remember that box you were pulling. We figured out that you did 250 joules of work on the box. So, if it took 2 seconds to move the box, then the average power output will be 125 watts. Again, we can also describe power in another way by putting two different facts together. 1. That work is equal to force times distance. 2. That average velocity is equal to distance over time. Knowing this, we can say that power is the net force applied to something with a particular average velocity. If you move the box 5 meters in 2 seconds, then its average velocity will be 2.5 meters per second. And we already said that you were pulling the box along with a force of 50 Newton. So, the force you were using to pull the box times the box's average velocity would also give you an average power output of 125 watts. The two equations for average power are really describing that same relationship, they are just using different qualities to do it. Well done, student. Now, let's go over to the assignment I have for you. Ensure to pause your screen briefly and copy down these questions. Assignment will help you master what you have been taught. We have come to the end of today's lesson. Before you go, let us summarize what we discussed earlier. Remember, we discussed the concept of work done. We also discussed the concept of power in relation to work done, as well as two different equations for calculating power. Alright, student. In our next class, we will discuss the concept of energy. See you in the next class.